introduce the company for those of you who may not be familiar with DECTRIS, tell you a little bit about our hybrid photon counting technology, quickly explain what it is and why it is beneficial for electron microscopy, give you a few examples to illustrate these benefits, and I think at the end there will be ample time for questions. I don't think my presentation will cover 45 minutes, so should we? Okay. And I realize I didn't even write my name on it, but I think you can read it here. My name is Sacha DeCarlo. I'm the Business Development Manager for electron microscopy. Since 3.5 years, I try to push DECTRIS together with lots of support from my colleagues into electron microscopy. So a few words about DECTRIS. DECTRIS started 13 years ago in Switzerland as a spin-off company from the Paul Scherrer Institute, so the Swiss light source. Today we're about 120 employees, and as you can see here on the left, a third of the company is really strongly focused on research and development. Since 2 years we have also a subsidiary in the USA, in Philadelphia, and starting actually maybe more next year, we will have also DECTRIS China. DECTRIS became established by providing hybrid photon counting detectors first to the synchrotron, for obvious reasons. The Swiss light source, sorry, was nearby. This is an example of a DECTRIS X16M, so big detector for macromolecular crystallography. But right after the introduction of the first Pilatus, we established a strategic partnership, for instance, with Rigaku, and our smaller detector, you see here also an Eiger, was integrated into home sources, lab diffractometers from Rigaku, Bruker, Mach experts, Anton Paar, and many more OEM partners. So this is the X-ray world, and as I said, since a few years, we're trying to look into electron microscopy as a new market, and we believe that we will be successful. Just to give you a bit of a history, so DECTRIS really revolutionized macromolecular crystallography and the way people collected data at the synchrotron. As you can see, I'm not going to go through all these milestones, but you may also know that all our detectors are named after Swiss mountains. Those of you who like to hike in the Swiss mountains, you may be familiar with the Pilatus and the Eiger. A few years ago, the Eiger 2 family of product was launched at IOCR in Hyderabad, and this set a very important milestone, because while Pilatus and Eiger were based on chips developed by the PSI, so the Paul Scherrer Institute detector group, we basically not only moved to new premises here in 2015, we also have our chip design group, electronics, and so Eiger 2 is based on a new generation of chips which are really designed in-house. And at M&M this year we introduced Quadrille, our first direct electron detector. I will mention this again later. And we here introduce 2 more direct electron detectors, and I will show you some application example. So hybrid photon counting is the official term at DECTRIS, but when you talk about electrons, the term photon may be confusing. So for electron microscopy, we refer to the hybrid pixel technology, and this in general, I will show you what it means, is the general term to explain that the detectors, as opposed by the famous Gatan K2, K3, the Falcon from FEI Thermo Fisher, and the direct electron, is not a monolithic active pixel sensor, but it's hybrid, and the hybrid name comes from the fact that you have essentially 2 elements. A sensor, a continuous sensor, which is sensitive to charged particles, so X-ray and electrons, you can see here as well. And underneath you have the readout chip. This is a CMOS-based. ASIC stands for Application Specific Integrated Circuit. Here you have the periphery where the signal comes out, and the contact between the sensor and the readout chip is an indium ball, which is represented here by this bump bond or bump pad. The charges, so X-rays or electrons, are captured by the sensor. Hole pairs are created, and you have a rapid drift thanks to a voltage bias or a field that is applied, such that the signals are rapidly drifted through the ohmic content, and here at the level of the bump pad. Then you have here the register of a signal. This is amplified, and this is then compared to internal calibration, so voltages, which is represented here by the comparator, and you have the ability, the user has the ability to set then an energy threshold, and if your signal is above this energy threshold, you get a digital count. If it's below, you get nothing. And I will come to that again with this later to explain a bit more in detail. So this energy thresholding gives you a mean to get this, what we call noise-free detection. Of course, there is a lower threshold, but in principle, what it means is when your detector is actually able, it's triggered and initialized, but you have no beam whatsoever. For a short exposure time, you really get a total number of count, which is 0, no readout noise, no dark current above this threshold. Of course, if you allow your detector to be running for a longer exposure time, you record cosmic radiation. But you can see here in the inset the type of traces which are created by cosmics, and it's very low counts, background, which can be eliminated by applying a threshold. So this is the general structure of the basic hybrid photon counting. So Pilatus and Eiger had a similar pixel structure. We introduced in Eiger 2 slightly more complicated in pixel electronics. So you have actually two comparators, so two threshold in principle. You also have two retrigger units and 2 times 16 counter per pixel. What or how does it work? This is an explanation of our DECTRIS instant retrigger technology. You have here on the graph 3 types of signal. There's a basic impulse, which is a certain intensity over this threshold. Here you have 2 events which are coming on the sensor, impinging onto the sensor in a very short time. So basically the signal remains above the threshold, but you have 2 events which are counted as 1. And here you have the typical situation which we refer to as pileup. You have a high influx rate of photons or electrons, and the signal remains above the threshold. And that's what is called a paralyzed counter in a normal hybrid pixel counting type of chip. So you have here several events, but the counter here would count 1 event here, also 1 event here, and also 1 event here. So we are losing counts at very high count rates. So what the logic here tells you, this is just to explain one more time, basically we have here this paralysis situation, and when the flux is really, really high in the multiple of mega counts, then your counter can only count once and never comes below this threshold. So the idea to introduce these retrigger units is such that to avoid this paralysis, what you can do is basically you reset the in-pixel electronics such that the counter can then count multiple times. And what you do basically during the time where the signal is above the threshold, you just need to count the number of times this retrigger unit is activated. So basically here you have an ability to correct the count rate. Of course, it's not going to be perfectly linear. I will show you later why. But here in this situation, that's the normal situation. You have one count. Here you have 2 events close to each other. You have to correct 2 counts. And in the case of a pileup, here you have 1, 2, 3, 4 events, and these are correctly counted. Of course, there is going to be a limit. But in principle, where with reintroducing the retrigger units in Eiger 2, we have a much improved count rate. So we're talking about mega counts per pixel per second. The counter is not paralyzed. This gives you a better count rate, gives you improved quality for the data. And I will show you what the curves look like for electrons. And this is it. So basically here we have a graph showing the incoming count rate in mega counts per second, and this is the measure rate. As I said, ideally you would want this to be linear, but when the count rate goes above 30, 40 mega count, With the retriggering off, you have a plateau here, and you have a limit above this. You cannot 5 times 10 to the 6. It's difficult to count, and in this case, you have, with the retrigger on, you can extend your count rate to about 30 megacounts. Of course, this it depends on a few factors. So this is the readout chip settings, the bias, the pixel size, of course, the surface, the total surface will influence this count rate. This is the ratio between the impinging energy of your photon or electron with respect to the threshold, and also what we call this multiplicity, that you may have at a certain energy and at a certain threshold more than just one count per electron. So this relationship, as you go to very high count rates, of course, this relationship no longer is equal to 1, but you may have, for this particular energy, 1.1 counts for electron, at 200 keV, maybe 2.2 counts per electrons, and so forth. How does that translate into application for electron microscopy? I will show you next. So, as far as EM products, we added 3 more new mountains, Quadro, ELA, and Cristallina, and I will proceed to show you what these detectors are and can do for microscopy. These products at the moment are mostly focused on the material science, TEM and STEM techniques because of the chip characteristics, but I will also show you some interesting results that were obtained for the life science cryo-EM people. So this is Quadro. You may have seen at the booth during the week. Is this detector here. It's our smallest of the detector, although the active area is 4 by 4 centimeter. This is about 500 by 500 pixel, because the pixel size is about 75 micron. The dynamic range is quite high. I will explain why I put here 16 to 32-bit dynamic range. As I previously explained, the count rate is pretty high. You can count about more than 10 megacounts or electron per pixel per second. With a window or a region of interest window, we are able to reach 18,000 frames per second. And the interesting part of the Eiger-2 chip is that it's compatible with a silicon sensor, but also high Z sensor for high energy or hard X-rays, and is of course radiation hard. Here are just a few examples where you can see that the direct electron beam is actually able to impinge on the sensor without the need of using a beam stop. And this is just atomic images and convergence beam electron diffraction example. So here is just molybdenum disulfide. This is this diffraction image here, shown at a slightly bigger magnification. The sample were the courtesy of Dr. Thomas Lagrange from EPFL in Switzerland. And as you have a look at the central peak, I'm zooming in now, you can see that thanks to this data technology, you can actually have here the direct beam, where you have close to, this is 1 frame, and then you have a very low counts around the main diffraction source and the diffraction beam. I'm zooming in one more time. Here it's showing, unfortunately the cross is no longer visible, but here is so the central beam, and these are the neighboring pixel with about 1,000 counts. And here you see, when you zoom in, this is the 1 frame, so this is the 4 central pixels are saturated, so that's the 16 beam counts, and then all around you have a very low count. And that increases really the quality of the data. If you then frame more than sum more than 1 frame, then you can extend the dynamic range up to 32-bit. In addition to electron diffraction, well, as mentioned here, there are other interesting techniques that this detector can be used with, and I'm pleased to tell you, for instance, that we have worked together with Nanomegas, who is giving a seminar next door, to integrate our detector into topspin, and this will allow you to do precession electron diffraction, of course also micro-ED, to do strain mapping, tachography for this stem, and this is a result that was recently obtained with a Libra 200 and our Quadrille detector for strain mapping. If you have questions at the end, I will refer to my colleagues, because I'm a life scientist, so I don't quite, I mean, I do understand what I look at, but if you have specialized questions, I may not be able to answer, but we'll get there. What is good, they tell me, is that with our detector you can get much faster and more reliable indexing, and that refers to the strain mapping. Together with Tim Grüne and Julian Wenmacher, who is here in the audience, we also collected, not precessing the beam this time, but by tilting the specimen and leaving the beam diffraction impinging onto the sample. They collected with our detector interesting data for micro-ED. Micro-ED is a technique that is in itself not new, so people have been using the ability to tilt the specimen stage of the microscope to collect data in diffraction. But here the interesting part is that you can bring crystals, single crystals, which are too small to be analyzed with synchrotron radiation inside the electron microscope, and with a quick workflow you get to solve the structure of single crystals. In this case it's paracetamol, so for drug, so it's interesting for pharma or structural chemistry. These results were published last year by Tim Grüne and his team in Angewandte Chemie, and the idea is that you can really go from the crystal and to the atomic model in a very, very fast and straightforward manner. If you look at the densities that you get with a single crystal, you might think that they're not good enough to be able to do atomic indexing, and I will show you other results which were obtained by Julian to counteract this impediment and come to data completeness which allows you to assign atomic density very precisely. This is just another example also from the chemie paper. I just wanted to show you this is another type of organic crystals. This crystals is lying here on fiber. I forgot which fiber. Help me, Julian. It's
the crystal is the fiber.
Right. This is lacy.
This is lacy.
All right. But you can collect diffraction pattern along the crystals, and here too, for this organic compound, this is a blue methylene derivative. This was done in about 4 hours. So what is important is that obviously your crystals is first of all absorbed onto a thin carbon film, so it has the tendency to lie flat and show one typical crystal direction. And while you tilt the beam, also the position of the crystal onto this film has to be somewhat ideal, because if it's too close to the copper wedge of the grid support, then you might have a limited angular space to cover. So there are obviously a few ways to counteract this. I'll come to that in a second. You can take advantage of the fact that sometimes the carbon film curls, so it's offering different orientation of your crystal, and by merging 3 to 4 data sets you get to data completeness, and here is what I wanted to get to. The other method is the introduction of these nylon fibers, which introduce a natural disruption of this network, and also here you have a way to distort the vision or the flat regularity of the carbon film such that your crystal is offered to you in different orientation, and you can collect data on a few crystals to reach the same data completeness with 4 or 5 crystals. The idea of merging then these 2-3 data sets is illustrated here. If you have only one data set, you might get the density, as I said, which is not precise enough to do atomic assignment to each of the density, and the angular completeness is also reduced. And as you increase the number of data sets that you can merge, or you cover a better angular space, then the densities become better and better, and in the ideal solution you then get really precise densities where you can do the assignments quite easily and also automatically, depending on the software you are using. So the Quadrille detector is, as I said, 500 by 500, and a few users expressed the wish to basically look at crystals which are a bit larger than organic compounds or small drugs, and that's why we also have a version which is 1000 by 1000 pixel or 1 megapixel, and this is the detector here on the left. We are also pleased to say that we worked together with the Boulder group, David Mastronarder and his collaborators. So for those of you who are using serial EM or serial D to collect micro-D data, both detector, all the Eiger-2 detector are compatible with this academic package. Here we switch technique. We collaborated together with Andrei Krivanek and his team from Neon, and we have delivered here this ELA. So this is a 500K. The surface, the active surface, is twice as big as the one from the Quadrille. It has a rectangular interface or flange, or the module has a rectangular shape, and this fits quite well for EELs. You can see here, this is the neon or neon iris spectrometer. So their microscope is actually upside down. It's based on the old VG design, so the gun is actually down here. This is a picture of an R&D microscope, and the prism is, and the filter is up here. So this is the prism. These are the lenses. These are two other retractable detectors along the way, and our ELA detector is here at the end. With this, they collected spectra. You can see here an example of boron nitride, one of the first EEL spectrum they collected. And Andre was very pleased because in one shot you can get the zero loss peak as well as other inner shell loss edges. And I will show you one example, typically with 100 to 300 picoampere, while being able to detect single electrons with a good DQE. So he was very pleased with that, and he also used this to proceed calculating elemental mapping. Sorry, this is the full slide. This is a slide that I stole from him directly. Here you have strontium titanate. You have here the zero loss peak image, and then a 5-second map and a 50-second. And you can see you have the zero loss peak resolved. This is titanium, and the nickel inserts or inclusion here you can see in the elemental map. This can be done quite fast because of the high speed of the detector. And here is another example where they did this comparison with some data published, I think hopefully in the meantime has been published. And you can see here this photon dispersal of angular momentum resolved EELs can take up to 3 hours because it's a labor-intensive technique. And if you do the same with neon iris and our detector, you can do that in minutes. And this paper is not published yet. All right. The last few slides I have for the life science cryo-EM. While we have been working to produce these detectors for the material science, we also collaborated since the beginning with Richard Henderson and Chris Russo at the MRC LMB. And as for the life scientists among you, you may be aware from the fact that they have been advocating maybe rethinking the theory for single particle cryo-EM. And there was a paper that was published at the beginning in February of this year in Ultra Microscopy, where they revisited the theory, and they proposed that for thin specimens, so 13 nanometer or 300 angstrom or below, when they are embedded in a thin film, 100 kV gives you actually a better information content than 300 kV or 200 kV. Of course, when you go to thicker specimen and you want to do cryo-electron tomography, in that case, the 300 kV energy is still your sweet spot. But for single particle cryo-EM, for small molecule, isolated macromolecule, 100 kV is better. And they already purchased one of our detectors a few years ago. This is a picture of Greg and Richard. Here at the beginning, we had the entire detector inserted in a vacuum chamber because they are built to be vacuum compatible. In the meantime, as you saw before, we changed how they look a bit, and we provided a better vacuum interface at the front of the detector. But they proceeded to measure the MTF and the DQE for various high tensions or energy from 40 to 100 kV. And as you can see here from the DQE curve at 100 kV, the energy that they are proposing for single particle, we already could show that our detector technology provides you with a close to ideal DQE curve. The next step was to measure real data sets and see how this looks in terms of reconstructing these various molecules. There's another paper which is in press, which is coming soon, but I'm allowed to show you a couple of results. So the new standard in cryo-EM, well, when I learned it, was tobacco mosaic virus, but things have changed a bit now. Apoferritin is the new standard sample. You can see a raw picture of our 500K. So you have 8 chips aligned in this rectangular shape, and we can do gain correction in such a way that you have here your field of view with 20 to 50 apoferritin molecule, but because of the pixel size, in order to be able to provide high resolution sampling, you have to work at a fairly high magnification, which then reduces your field of view, and then you have to collect eventually a lot more data. But this was just a proof of concept. So what they did is collect data on a Tecna EF20, but reduce the high tension to about 100 kilovolt. And they tested this, as you will see in the paper that is coming. They tested several data sets. The largest macromolecule was hepatitis B capsid virus. You can see here an example. Of course, with the reduced field of view, you have only a few viral particles, so you have to collect a bit more data. And at the end, with a 2.7 angstrom sampling per pixel, they got about 8 angstrom resolution. But one of the interesting results, and this is maybe a response to the poll that we put on Twitter, this was one of the smallest molecule they analyzed. So this is DPS, a DNA binding protein for starved cells. It's only 8 nanometer in diameter, about 220 kilodalton. You see here a field of view with the reverse contrast for those of you who are used to look at this cryo-EM image. And here, with 17,000 particles and a 1.4 angstrom per pixel sampling, they reached a 3.4 angstrom resolution, which was a very pleasing result, because I was not expecting anything better than 5 for 100 kV and such a small particle. So these are very encouraging results, and this is the paper I mentioned, which should appear very soon. So, as a summary, I just wanted to stress one more time that we design our chip technology in-house. So in our detector, you will not find any Medipix or other type of chips. We introduced 3 new direct electron detectors based on the Eiger-2 new technology. These detectors, I think, provide a really great dynamic range, high-speed continuous readout, and they are, of course, radiation hard, and we expect to see more interesting results in the material science application domain. We showed that also this detector technology has a close to ideal DQE for single particle cryo-EM at 100 kV, so we hope to see more results going in that direction and maybe convince the manufacturer that this technology is worth exploring further. We also work with various partners to perform software integration, which allows seamless operation. So we have now Neon Swift for the material scientists. It's open source, as I mentioned, Serial-EM, Topspin, and Nanomegas, but we also can provide a standalone solution for those of you who are familiar, maybe the crystallographer, with our Albola viewer. And we are offering support via our DECTRIS headquarters, so Switzerland, all over Europe, DECTRIS USA, and as I mentioned, maybe from next year, DECTRIS China. Here is a team that was here at MC, and thank you very much for your attention.